So now we're going to move on from sorting to talk about a different problem, that of searching. We're considering the abstract data type, which is often called dictionary or table. This is basically a simple way to implement a database. The key operations we have are 3 in number. We have some kind of data structure, some object, it has elements in it. So typically these elements are described by keys in the same way sorting was. You could have a huge data record, for example, representing a customer of a bank with all kinds of details, and we might be searching by surname, something like that, or phone number. So the basic operations are to insert an element, to find an element with a given key, and then retrieve the record that's associated with it. And finally, we want to delete sometimes. These are the 3 basic operations. And there are many ways to implement such an abstract data type, and we'll discuss some of them here. The 2 main ideas that are used in practice are various types of binary trees, binary search trees, and hash tables. And we'll talk about both of these in the next few lectures. But let's start with a really simple, naive implementation, just a list. So suppose I start with the simplest thing, an unsorted list. It could be an array or a linked list implementation. Insertion is easy. I just stick it at the end. Of course, whenever you have an array-based list and you keep inserting, eventually you make it full. At some point you'll have to resize and copy everything to a different array. It turns out if you do that cleverly, you can make the average amount of time for doing that very small. I'm not going to go into that here. Let's assume we have a list that's not going to be over full. We can just insert at the end in constant time. We can also insert in constant time, obviously, with a linked list, because we just stick the pointers in the right place. So insertion is quick. However, find is very slow. As we already know, the best you can expect to do here, similar to what we were ending up doing with selection sort, is just to search all the way along one by one till we've seen everything, in other words, order n. And deletion is hard work as well, even if you know where you want to delete an element. So suppose you want to delete this element in here. If you have an array implementation, you can go straight there, but then to delete it, you have to move along all your elements to the right, and in the worst case, the element could be here, and you have to shuffle everything back along. So it could take order n time in the worst case to delete. If you have a linked list implementation, it's not so hard to rewire all the pointers, but you can't just go straight there. You don't have random access. You have to start at the beginning of the list and follow the pointers till you even get there and then start moving stuff. So again, it can take order n in the worst case. So for unsorted lists, insertion is quick, but the other 2 operations are slow. Now let's consider a related idea, a sorted list. Here we have some improvements with the find operation. Insert is a lot harder because you can't just insert something at the end. You have to insert it in the right place to maintain sortedness, and you're basically doing the kind of work that insertion sort does. It's very slow. It's going to be order n in the worst case to insert an element. Deletion is also going to be difficult for the same reasons we had before, shuffling things along in an array or scanning along the pointers. Finding, however, can be done more efficiently, and it can be done using the idea of binary search. So just to remind you of this, which you're probably familiar with, if I have a sorted, let's say an array to make it even simpler, sorted list, I'm looking for a particular key element in there. I go to the middle, the median index element. If it's an even size one, then I choose one of the two. Let's say choose the first of the two median elements. If it's odd size, there's a unique choice for that. And then I check if the key that I want is here, then I'm done. I just report that it's there. That's all I'm trying to do. Find. If the key that I want is bigger than this, then I go to the right and recursively, essentially, look only at that half and redo the entire procedure. If the key that I'm looking for is too small compared to this one here, then it must be lying to the left, so I go to the left and apply it recursively. If you think about the running time, the search space here is halving at each step. So the amount of work I need to find something is only the little bit of overhead I had to do in order to do the one comparison to check with the median there. And then I only have to look at one half of the resulting array. Using the techniques for solving recurrences that we've already seen, you can easily show that the running time is the order log n. So here's some pseudocode for binary search. We have a list of size n containing keys, and we have a specific key that we're looking for, may or may not be in the list. We start with left and right pointers at the ends of the lists, seen in line 2 and 3 here. Then we have a loop. As long as the left pointer hasn't crossed the right pointer, we calculate the median index of the two pointers. So if the range from L to R inclusive is even in length, for example, L is 2 and R is 7, then M in that case would be 4. We're rounding down. So now we have the median index. We access the median element. If it's smaller than what we want, then we certainly haven't found it, and we know that it must lie to the right because of the sortedness of the list. Otherwise, if the element at M is too big, we can push the right pointer down to deal with the left sublist only. And the other case is if A of M is equal to K, in which case we found it, and we'll just return M. So if the key K occurs more than once in the list, we will only find one instance of it with this algorithm. That's usually okay. And if we fall right down to the bottom line, that will happen if the while loop terminates, and that will happen when the pointers cross over. That shows that K is not in the list, and so we will just return -1. Since we're returning the address where the key can be found, if it can't be found, -1 is a good choice, since the real index must be between 0 and n-1 inclusive. It's very easy to get this algorithm wrong by making off by 1 errors. In line 5, 7 and 9, things could have gone wrong if we weren't very careful. But it turns out, with the way we've done it here, if K is in the list, it'll be caught inside an interval which gets smaller and smaller. If it hasn't been found before, line 11 will execute when L is equal to R. Now, there's quite a nice relationship between binary search in a sorted list and a specific type of tree. So suppose I have a sorted list. I'm going to use some letters here, which probably means something to you if you've played Scrabble. That's my sorted list. When I'm trying to search for a key, what I do is first go to the median element here. I'm going to write it below like that. And then depending on whether I want to go smaller or greater, depending on whether I'm looking for a B or a Z, for example, I branch either to the left or to the right. And then depending on whether I want to go smaller or larger, I branch like that. We can fill in the right hand side in a similar way. So the execution of binary search algorithm on this list can be described by a particular type of binary tree. And this binary tree has some nice properties. You'll notice that all the small keys, the ones early in the ordering, are in the left subtree. Then the middle one is at the root, and then the right-hand subtree has the larger keys. And this happens recursively all the way down. Small, middle, large. If you know what the in-order traversal of a binary tree is, it's easy to see that the in-order traversal, which first does the left subtree, then the root, then the right subtree, and works recursively from the bottom up to the top, that traversal is going to visit all the nodes in the correct order. You're basically going from left to right across the tree with that in-order traversal, which corresponds to this ordering here. So there's a clear correspondence between how binary search works and this particular type of tree, which is what's called a binary search tree. So now I want to switch and think about a binary search tree as being an explicit data structure. It's something that stores the keys in it. We're going to use it to implement the dictionary. So it's no longer describing the action of an algorithm. It is an explicit data structure. It's a binary tree which doesn't have to be left complete. It doesn't have to look like a heap. It contains keys from some totally ordered set. The defining property is that if you have a key anywhere in the tree, then every key in its left subtree is smaller than this key at the node, and everything in the right subtree is larger. So to go smaller you branch left, to go larger you branch right, just as we did before. That's the definition of a binary search tree. You can store the data there anywhere you like, as long as you satisfy that property. And for a given set of keys, there can be many different trees with that number of nodes, with different shapes, which all work. For example, if I have those keys that I looked at before, well, I could have this tree, big long degenerate tree that goes down like that with height 6. Or I could have the nice balanced looking tree that we had before with n at the root and two subtrees of size 3. That had a much smaller height, namely 2. Each of those would be valid binary search trees, but some of them are better than others if we want to have good performance. So what we're doing here is looking at the binary search tree as a way of implementing the dictionary. So we need to understand how we can insert, find, or delete elements from a binary search tree. Well, suppose you have a tree that's already got the nice binary search property, and we want to find an element. We just use binary search. We start at the root. If we found the element already, we stop. If not, and the element we want is bigger, we branch to the right, otherwise we branch to the left. And then we just recursively go down the tree. Either we find it, or we find where it should be, but it isn't. So for example, if we had our tree like this, the one we had before, with the AEI NRST, but R was somehow missing, then we would search. We know it's got to be bigger than N, but it's less than S. We would look for it, and it's not there, so we would know it's not in the tree. And find is very quick if the tree is nice and balanced, because all you have to do is go down at most the height of the tree. But of course, if the height of the tree is very large, in the worst case, things could be really bad. It could take order n time to find something in the worst case. In general, the time it takes to find something in a binary search tree, or to be sure that it's not there, is the order of the height of the tree in the worst case. But unfortunately, if we use badly chosen trees, that height could be really quite large. So we see it's going to be important to control the shape of our trees if we can. But let's go on and see some of the other operations, because they're not quite so obvious. Start with insertion because it's easier. If you want to insert something that's not in the tree, you use find to find where it would be if it were there, and then you put it there. In this tree, if I want to insert the letter R, I just branch to where it should be. There's a gap, so I put it in. I can always do that. In this case, suppose I want to add something here, any letter that's not one of the 7 that I chose before. A, E, I, N, R, S, T is the tree. Yeah. If I get to the bottom of the tree, suppose it was a Z, it would just go there. It either goes left or right. You can always add an extra pointer somewhere. So insertion is not difficult, really. It's a little bit harder than find, but not much work. And the basic issue here is that it's going to take about as much time as the height of the tree as well, because it might be that the natural place to insert is right down the bottom, and you have a tree with a very large height in the worst case. And in general, it takes order H, where H is the height of the tree. So those two are okay. Now deletion takes a little bit more work, but not too much. Basically, we search for the node, we find it. If it's a leaf node at the bottom, has no children, then we just delete it. That's simple. We can delete anywhere. Unlike the heap situation, we can delete anything we like, anywhere, and not worry about the shape of the remaining tree. What if we want to delete something that has a child, but just one, for example this node E here? Well, it's pretty clear to see what we can do. We just delete it, and we replace that with that. What that really means is that A moves up to where E was. Essentially we swap them if we like, and then we just are in the previous case where E is a little lower down, and we delete it. If we have a bigger subtree, it's still okay. We just move everything up. And the binary search tree property is still maintained. All these keys are in the right relative order to each other and to here. However, if we try to delete a node that has 2 children, then a bit of work is required. Suppose we want to delete this one. What we want to do is replace that with something in the subtree to become the root of that tree. If you think about how to do that, you have to be careful. Whatever's up there has got to be smaller than everything down here and larger than everything over here. And an obvious way to do that is you search through this subtree, find the smallest possible element in there, smallest key, put it up here. It's in the correct, it's still larger than everything here because it was larger than this one, and that was larger than that. So you have the correct ordering over here, and you have the correct ordering here because it was smaller than everything in this tree. So that will work. The question is, how long does it take you've got to find the smallest element here. Well, it doesn't take that long because we know from the shape of the tree where it's going to live. You can see here that the smallest element in a binary search tree is going to be way over to the left. And you can just follow links down until you find it. So when we want to find the smallest element in this subtree, we start at T and we go down to the left until we stop. That takes time at most the height of the big tree. So again, order H is the right running time there. So all these basic operations, it turns out, run in time order the height of the tree. And so it will be very important, as I said before, to ensure that we have some kind of control over the heights and we don't run into this nasty case. Because if we're going to have to do order n for these basic operations, why not just use a standard list? So here we are with the questions again. We've got 3 basic ones. The first one deals with the deletion method that we used in binary search trees. We decided to delete a node with 2 children by going to the right subtree and finding the smallest element. What would happen if instead we went to the left subtree and found the largest element? So think about that and the consequences of that. The next question relates to average case analysis. We know that if we're unlucky or silly enough to have a binary search tree that's very long and thin with a large height, we might end up doing a lot more work than we really want to. But how likely is that? Usually we start off with no elements in our dictionary and we insert them as they come. One by one we might delete some, but we basically grow the tree over time. How likely is it that we're going to get such a strange shaped tree? So you might want to do some analysis here for small values of n. 3, 4, for example. For example, n equals 3 and 4. Try and look at all the possible ways that keys could be presented and inserted. And see how often you really get these very unbalanced trees. On average, what is the height? Finally, we're dealing with a problem of searching. We have keys which come from a totally ordered set, so we're in the same setup we were for sorting. We're looking at various types of trees, such as binary search trees. They look somewhat reminiscent of some of the things we saw in sorting. What actually is the relationship exactly between binary search trees and sorting? So think about all these, and we'll see you next time.